All right, so let's do some example problems with forces in motion. So we're going to start with something very, very simple. If I have a wagon and it's got a mass M and we're pulling it with a force of F. All right, this is about the easiest problem you can get. No friction, no air resistance, anything like that. All right, and I want to know what is the acceleration of my wagon. I don't think you really have to draw a free body diagram here. This is a very easy problem, but we're going to draw one anyway, just for the practice. So there's your wagon and the forces on this thing. We have the force F that's pulling. Also, there is, of course, gravity pulling down on it. And to counter that gravity, the ground is pushing up with a normal force there. So in the y direction, we get normal force equals gravity, right? Normal force up minus gravity down equals 0 newtons. We don't need that for this problem, but it is true. And that'll come into play when we do problems involving friction. That's going to become important. But in this case, in the x direction, everything to the right, only forces to the right. Everything to the left, 0. And the answer is, well, is it in equilibrium or is it accelerating? It is accelerating, so we're going to write F equals ma. It's just Newton's second law, folks. And so that's your equation. Plug in whatever numbers I gave you, and you're done. And we're going to make things slightly more complicated. We're going to take a wagon of mass m. Now we're going to pull it. This is more realistic, right? To pull it at an angle. Most of us don't pull a wagon straight ahead. That would be a little strange. So we have our, there's a motorcycle going by. So we have our force and our angle, and we want to then set this thing up again. The free body diagram is force at an angle, gravity straight down, and normal force straight up. Let's do the x direction first, and then I have a comment about the y direction. In the x direction, what forces are pulling at least partially to the right? The force, the x component of the force. That's it. Nothing is pulling to the left. And is this thing accelerating? Well, I'm asking you to find the acceleration, so we can assume that's probably the case. Fx equals ma. Fx is F cosine theta equals ma. Divide the m over, we get a equals F cos theta over m. Plug in your numbers and you're done. Cool, huh? Very fast, pretty easy. These are easy problems. In the y direction, things are a little more complicated. It doesn't matter for this problem, but we'll need it later and it won't hurt you to see it twice. In the y direction, everything pointing up. The normal force is pointing up. There's also a bit of the force that we're pulling with pointing up. Anything pointing down is gravity, right? And this is going to give us, well, it's in equilibrium in the y direction, right? It's not accelerating. We're not yanking it off the ground, right? We're not jerking it down into the ground. So this is going to be 0 newtons for equilibrium. If we solve this for normal force real quick, you're going to see something. Normal force is going to equal the force due to gravity minus the force that we pulled with. That should make good sense. The floor has to support it less because we're pulling up on it, right? So the normal force is equal to mg minus F sine theta. If the normal force decreases, that means that what we gain by pulling up at an angle is that we've reduced the normal force, which means we've reduced the amount of friction. All right? That's problem number 1. Problem number 2. Okay, so suppose we have a student standing here and he's 80 kilograms. That's a 0. And standing a whopping 2 meters away is another student, and she is 50 kilograms. And the question is, how gravitationally attracted are they to one another? This becomes a really easy problem if you realize that, well, you can't use weight equals mg. Neither one of them is the planet Earth. So you have to then use Newton's law of universal gravitation, which is just Fg equals big G, m1, m2 over r squared. The most common problems that people have in solving this type of problem are bookkeeping wise. They forget to square the denominator. That's number 1. Number 2, they don't write in all their units properly and they lose credit for things. So that one is no fun. If to solve a problem and get the correct answer and then lose credit because you didn't include the right units, don't do that. Don't be that person. All right. Force due to gravity is G. Look that up on your reference tables. It's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Put that in parentheses. Next, 80 kilograms is M1. M2 is 50 kilograms. Notice it doesn't matter what order you put these in. And then divided by, the distance between them is 2 meters. I strongly suggest putting that in parentheses because otherwise it's way too easy to forget this square. If I was to rewrite this the bad way and just say 2 meters squared, it's way too easy to gloss over this and not realize that that's not a unit of meters squared. That is 2 meters quantity squared. Plug in all these numbers into your calculator. Make sure you do it right, and you're going to get a huge number here. You're going to get 6.67 times 10 to the negative 8, and the units of force are newtons. That is, I was kidding. It's not huge. It's a very tiny amount of attraction, which is exactly what you'd expect. You'd never notice this. This is going to be totally overwhelmed by any kind of frictional forces and stuff like that. All right? It's that easy. Okay, so this here is a classic physics problem where you're hanging a stoplight. You need these wires at an angle to prevent it from swaying side to side too much. And the deal here is if you were getting paid to design and build these, if you make them not strong enough, they're going to fall and hit cars and people and things, and that's going to be terrible. And if you make them too strong, it's going to cost you too much. You're going to get outbid and no one's going to hire you. So the goal is to figure out what is strong enough. And the way to do that is you'd create a forces problem like this, figure out your answer, and then maybe double or triple that answer just to be safe. All right, so here goes. What we have here is we're going to draw a free body diagram of that spot right there. And I'm going to name the tension in each of these ropes. Let's call this one T1, and this one T2, and this one T3, because we're super creative. All right, so the free body diagram is simply T1, T3, and T2. It's not perfect. This tablet is hard to draw on. And this is 60 degrees, and this is 30 degrees. There you go. That's our free body diagram. So now we need to solve for the tension in each rope. I'm going to draw a free body diagram of our 10 kilogram stoplight here too. All right. It has weight, the force due to gravity pulling it down, and it has the tension of the rope pulling it up. That makes T1 super easy. This equation in the y direction, we have anything up, tension, minus anything down, force due to gravity, equals, is this thing in equilibrium? Well, it better be. If it's accelerating, there's a real problem. So this is going to be 0 newtons. And so tension 1 minus mg equals 0 newtons. And so tension 1 just equals mg. And that's 10 kilograms times 9.81 meters per second squared is 98.1 newtons. Although I'm not as worried about getting the actual numbers as I am the formulas when we do these types of problems. All right, so coming over here, that gives us a couple of things. So in the y direction, we can create an equation. Upward, we have the y component of T2. We also have the y component of T3. And that's it, upward. Downward, we have T1. And it's definitely in equilibrium again. Notice here, I did not give you the angles with respect to the horizontal, so you have to be careful in this type of situation. The y component here is adjacent to the angle in both cases, and with adjacent you use cosine. So this becomes T2 cosine of theta plus T3 cosine of phi minus, this is mg, well that's a known now, equals 0 newtons. Here we have T2 is an unknown, theta is known, T3 is unknown, phi is known, m and g are known. So we still have two unknowns, T2 and T3, so we can't finish the problem yet with just that equation. In the x direction, what do we have? Anything to the right, we have t3x. Anything else to the right? No. To the left, we have t2x, so minus t2x. And is this thing in equilibrium? It better be. So we get t3x, which again is going to be the x components of these triangles are opposite the angles, so we're going to use sine. This is t3 sine theta minus t2 sine, I mix those up, t3 sine phi minus t2 sine theta equals 0. I'm just going to flip that over to the other side. Now, we have the same two unknowns here as we do here. It's just a matter of solving for one thing and substituting in to find the other. Let's solve for t2 here. We'll say t2 is equal to t3 sine phi over sine theta. Take that, plug it in up here, solve, and you're done. Okay, so here's a problem with a mass sliding down a ramp without any kind of friction. And this problem quickly looks like it's going to be terrible, but it turns out to be very manageable with one very important trick. All right, so here's what makes it look terrible. If we draw our free body diagram for this thing, we say here's our mass, and what forces do we have acting on this object? We have gravity pulls the thing straight down, right? Gravity doesn't pull down a ramp. It pulls straight down. And, well, it's not sinking into the ramp, so we have a normal force. Remember that normal means perpendicular, so the normal force is this way. This looks gross. It's moving this way, right? But it's... none of the forces are... What the heck do we do? All right, there's a trick here that we're going to use that's going to make this whole thing significantly easier. You ready? We're going to tilt our heads. Okay, we're going to tilt our heads like this, and we're going to look at it at an angle. And by tilt our heads, what I mean is we're going to tilt our axes. There is no rule that x has to be horizontal and that y has to be vertical. So we're going to put our x-axis here and our y-axis here. And when we do that, this becomes significantly easier. Labeling an angle on this is a fun part here. So let's look at this triangle here. This triangle here, this is the angle theta, right? So that means that makes this angle 90 minus theta. This is also 90 degrees, which means, and if this is 90 minus theta, then this also has to be theta. So let's back that off here. And we're going to say this here is our angle theta. With our tilted head, this free body diagram becomes way easier. The whole problem is a lot simpler. Let's look at the x direction. In the x direction, what do we have pointing at least partially this way? We have a component of gravity. We have the force of gravity in the x direction. Do we have anything pointing this way? We don't. So that's nothing. Is it in equilibrium? It better not be. It's speeding up, sliding down the ramp. And so this thing is equal to ma. Let's take a look. The component in the x direction is opposite of the angle, and that means we need to use sine, right? So this is going to be force of gravity sine theta equals ma. That's mg sine theta equals ma. Nicely. Masses cancel. We don't care what the mass of the object is. It could be a ball bearing. It could be a Mack truck. It doesn't matter. And so the acceleration down the ramp is g sine theta. From here, you can use any kinematics equations that you want in order to figure out how fast it's going. Say you could use vf squared equals vi squared plus 2ad. Or you could use vf equals vi plus at to figure out its speed at the bottom. You could use d equals 1/2 at squared to figure out the time it took. There's all those kinematics equations you can use once you have acceleration. Cool, huh? All right, side note, in the y direction, gravity and normal force are no longer equal to each other. You have the force, the normal force is in the positive y direction minus the y component of the gravity. It is in equilibrium in the y direction. It is neither sinking into nor springing out of the ramp. So this is 0 newtons. So the normal force in this case minus this is going to be Fg cosine theta equals 0. I'll move it over to the other side. And so normal force is equal to mg cos theta. We don't need that right now, but when we add friction to this problem later, we're going to need that. Okay, next up we have what we call Atwood's machine. Atwood's machine was used a long time ago for construction purposes. If you have something big and heavy that you want to bring up to the top of a building, you'd set up a pulley, throw a rope over it, and then you'd bring up bricks or something that's a lot lighter, put them on a platform, and then as the one platform fell, the other one would come up, and you would end up with a slower, much more controlled motion, especially once you add friction, which we're going to ignore. So that's what this is. This is Atwood's machine, and this is a classic physics problem, and it's going to really help us here show what a pulley does when it comes to doing the math. You learned in elementary or middle school that what pulleys do is they change the direction of a force. And that's true. It'll take the tension here and wrap it around this pulley. What we need to do is figure out a direction of motion. And it looks to me like if big M is heavier than little m, when we let go of this thing, big M is going to fall and little m is going to rise. So the direction of motion is this way. So that is going to be positive. When we are creating equations for our free body diagrams, on this side, up is positive and down is negative. On this side, down is positive and up is negative. If we don't do that, we'll get wrong answers, and that's no bueno. All right, so let's look for mass M. Let's draw a free body diagram. Pretty simple. We have gravity is pulling it down, and this is going to be Fg1. And then upwards, we have the tension in the rope. That's it. For mass big M, gravity is pulling it down. And we have the same tension because it's the same rope. A rope is going to have the same tension all the way throughout, or at least close enough for Regents and AP1 purposes. All right, so we have our two free body diagrams, and now we want to make some equations. And so in this case, in the direction of motion, we have tension, that's positive. Opposing the direction of motion, we have the force of gravity, and this thing is going to be accelerating, and so this is little m a, it's not in equilibrium. For this one, we have in the direction of motion, we have the force due to gravity 2. Opposing that, we have the tension, and this thing is going to be accelerating. It's not in equilibrium, so it's equal to big M, A. Now, we have how many unknowns? We don't know the tension in the rope, and we don't know the acceleration. Same thing over here. Two equations, two unknowns. This is a totally solvable problem. I'm going to rewrite these real quick. This is going to be tension minus little mg equals little ma. And over here, this is going to be big mg minus tension equals big ma. One of the neat things you can do is you can actually add equations together. I can just take this whole equation and put it over here. And so I can say mg minus t equals ma. And I'm going to add these two equations together. The tension plus negative tension cancels out, and then we get big mg minus mg equals little ma plus big ma. Cleaning that up a little bit, let's factor out a g. And let's factor out an a. And we'll come up over here. And we get A equals G times the difference of the masses divided by the sum of the masses. This is called Atwood's equation for Atwood's machine, and it behaves as you would expect. The bigger the difference between the masses, the faster this thing is going to go. Doesn't that make good sense? Right? And then the total mass is going to make the whole thing go slower because larger masses are harder to accelerate. So there is Atwood's machine. Okay, so this next one is similar to Atwood's machine. We have a table with a pulley on it, and we have we have a cart and we have a mass. This cart is going to be accelerated when we let go. It's going to move a distance d and then hit the pulley. The question is, how fast is it going when it hits the pulley? No surprise here, we're going to start with free body diagram. We have tension pulling this way. We have gravity pulling this way. We have the normal force pulling this way. There's no friction or anything in the problem, so the y direction is going to be completely irrelevant, and this gives us a really easy equation. We have F equals ma. All the tension is to the right, nothing is to the left. This thing is not in equilibrium, so it's going to accelerate. Tension equals ma. Easy, but we don't know the tension. So we have to come over here and look at this free body diagram. This thing has mg down, right? We have force due to gravity 2 down, and up we have the tension. It's the same tension. This is similar to Atwood's problem. It's also similar that we have a pulley, and this is the direction of motion. So in this case, down is going to be positive. We get the force due to gravity of this thing minus the tension upward equals, it's not in equilibrium. This thing's going to be big M A. This is big mg minus T equals big M A. Move the T over, solve for it, right? So we get T over there equals big mg minus big Ma, right? And we can now substitute wherever we want to. We could substitute this thing in over there. Probably looks a little easier, doesn't it? So we get big mg minus big Ma equals little m A. And I guess I shouldn't have moved that thing over, because now I can move this over here, add big Ma to both sides. We get mg equals A times the sum of the masses. And so A is going to equal big mg divided by big M plus little m. That tells us that the bigger this hanging mass is, the faster it's going to accelerate. That's good. And it tells us that the more combined mass the whole thing has, the bigger little m is, the less it's going to accelerate. That also makes sense. So this looks like a good answer to me. Plug in whatever numbers you're given, and you're all set. We have two blocks. They are attached together with a cord right here with an unknown tension, and they're being pulled with a force of 80 newtons. There's a specific thing I want you to get out of this particular problem, all right? We can draw not one, not two, but actually three free body diagrams here, because we can treat this block as a system by itself. We can treat this block as a system by itself. And because they'll be moving together, we can treat the whole thing, this block, cord, block system, as a system as well. And each of those is going to yield some slightly different free body diagrams and slightly different equations. That's a lot of tools for you to be able to use to solve problems. So let's take a look at this one. We have force due to gravity is mg and a normal force up. And pulling it to the right, we have a tension. That's all we have. For this one here, we have 80 newtons pulling to the right. To the left, we have tension. It's got some weight here, M1G, and there is another normal force. I probably ought to call that one 1 and that one 2. The whole system, treating this as one object, we have the force pulling to the right, nothing pulling to the left, a total force due to gravity, I'll call that 3, and a total normal force. And none of these y directions matter, so to save time, I'm going to ignore them, all right? This gives us a bunch of different equations. This one over here gives us tension to the right minus nothing to the left equals ma, that's M2A. This one gives us force to the right minus tension to the left equals, this is, again, ma, M1A. Over here, this one gives us force to the right minus nothing to the left equals M1 plus M2, the total mass of the system, times A. Pick any of those and solve for A. This is probably the easiest one. You know that's 80. You know both of these. You can plug it and solve for A here. Down here, you could then plug this A in here. And the only thing you don't know is tension. You could solve for tension. Or you could have plugged it in here and solved for tension that way. Any of those work. Draw your free body diagrams. You can do it for individual pieces of the system, and you can do it for the system as a whole. Okay, so this problem is a hockey puck that is sliding along with an initial speed of 10 meters per second. We're not going to worry about the numbers here, but it's on a frictionless surface, very smooth ice. And then at some point it hits some rougher ice, and it slows and stops in 60 meters. The question is, what is the coefficient of friction of this ice? You ready? Let's draw a free body diagram of the hockey puck when it's moving on the frictionless ice. Clearly there is some gravity downward, and there is a normal force upward. It's moving to the right, but nothing is pushing it to the right. There's no forces to the right, but friction is slowing it down, so we have a force of friction to the left. Yes? Okay. The direction we're interested in is probably this one, so we could start in the x direction and say nothing to the right minus force of friction to the left equals, is it in equilibrium? No, it's slowing down, so equals ma. We're in good shape so far. We know the equation for the force of friction from our reference tables. Force of friction equals mu times normal force. And this equals ma. Cool. We don't know the normal force at the moment, but it is in our free body diagram. So let's pop over here to the y direction and say upwards is a normal force. Anything else upward? No. Downwards is gravity. So we've got gravity down and nothing else down. Is it in equilibrium in the y direction? Yes, it's neither sinking into the ice nor springing off of the ice. It's in equilibrium. So this is going to be 0 newtons. So this is a flat horizontal surface, and you already know this. Normal force is equal to force due to gravity, which is mg. So we can come back over here and put in mu mg equals ma. These masses cancel, which is cool. That means it doesn't matter whether it's a hockey puck or a truck or whatever. And then, so the acceleration here is equal to minus mu g, or mu is going to equal minus a over g. I want to talk about this for just a second in terms of vehicular safety. When you have a great big truck in the wintertime and you're driving around, that weight, that mass of the truck helps you go. It gives you more traction when you're going. It gives you more traction when you're stopping too, but you are exactly proportionally that much harder to stop. That's what this canceled mass means. So having a big, heavy vehicle does not help you stop in the wintertime. And that is really important when it comes to safety. Now let's revisit an older problem and make it more realistic. This is our cart being pulled at an angle, only now there is some friction. You ready? We're going to start, as I'm sure will shock you, with a free body diagram. So we're going to draw our force there at our angle theta there. We're going to say, all right, there is friction. I just told you that. And there's a little mu over here, right? Coefficient of friction. So there's a force of friction. And we have gravity downward and our normal force upward. You can see that this free body diagram is more complicated than anything we've drawn so far, but all you're really doing is counting arrows anyway, so it's really not that big of a deal. Let's take a look. In the x direction, we'll come over here for the x direction. In the x direction, to the right, we have the x component of f, which we'll call fx. Anything else to the right? No. Anything to the left? Yes, we have our force of friction to the left. Cool. Anything else to the left? No. Is this thing in equilibrium? The honest answer is we don't know. It could have an acceleration of 0, but if you don't know, then you say it's not. And then if you solved and got an acceleration of 0 later, then, okay, you'd know it was in equilibrium. All right, so fx minus force of friction equals ma. Cool. That's our basic equation. We can plug in our specifics. Fx is f cosine theta. Force of friction is mu times normal force, and ma is ma. All right, we're getting there. F was given, theta is given, mu is given. Normal force we do not yet know. M was given, A was given, or A is what we're looking for. So normal force. To get our normal force, well, it shows up in the y direction, right? I wrote that wrong, didn't I? That's a normal force. That's Fn. All right, so normal force is in the y direction. So in the y direction, what's pointing upward? The normal force is pointing upward. A component of our pull force, F, is pointing upward. And that's it. Anything pointing downward? Yes, we have a force due to gravity downward. Anything else pointing downward? No. Is it in equilibrium in the y direction? Yeah, we're not yanking this thing off the ground. It's not sinking into the ground, so it's in equilibrium. So normal force is going to equal the force due to gravity minus Fy. I just moved these over to the other side. So normal force is equal to force due to gravity is mg. Force in the y direction is F sine theta. So we can plug in, get our normal force, plug it in there, and solve. Or we could take this and plug it in and then solve. F cosine theta minus mu times all that stuff. Mg minus F sine theta equals ma. It's big, it's gross, it's ugly, but it's solved. Plug in all your numbers, you'll get yourself your answer. All done. Okay, now we have a block on a ramp and we're going to add friction to it. We're going to do that same trick where we tilt our axes too. So we have the force of gravity straight down. We have the normal force perpendicular to the ramp because that's what normal means. And then we have friction up the ramp opposing motion. So in this first question, I'm going to say this thing is in equilibrium, all right? It's not moving. So my question is, what coefficient of friction is going to prevent it from moving? Obviously, if there were no friction, then it would slide down the ramp. What is the minimum coefficient of friction necessary for this thing to not move? So our trick, we're going to tilt our axis. We got our x-axis here, and we're going to have our y-axis here. And as we figured out before, the angle that gravity makes with the y, our new tilted y-axis, is the same as the angle of the ramp. So what is going in the positive x direction? That is this component of gravity, right? So in the x direction, we have that component of gravity. Anything else in the positive? No. Negative? Yes. Friction. So minus force of friction. Anything else in the negative? No. Is it in equilibrium? Yes. So this is 0 newtons. Force due to gravity, remember this is opposite the angle here, so that's going to be sine. This is going to be mg sine theta minus force of friction is mu times normal force equals 0 newtons. I'm going to just move that to the other side because that makes our life a little bit easier. Let me erase that little blob. There we go. All right. Now, so we have mg sine theta equals mu times normal force. We don't know the normal force at the moment. It is not equal to the force due to gravity. We need the y direction to find that. We did this once before, but let's do it again. In the positive y direction, pushing out of the ramp, we have the normal force. In the negative y direction, pushing into the ramp, we have the y component of gravity. It is in equilibrium. It is neither springing out of nor sinking into the ramp. So we get normal force equals, I'll move that over to the other side, the force due to gravity in the y direction is mg times, that is adjacent to the angle, adjacent we use cosine. So normal force is mg cosine theta. Take that, plug it in, take this, plug it in here. We get mg sine theta equals mu mg cosine theta. M's cancel. That's cool. G's cancel. That's super cool too. Doesn't matter what planet we're on. Cosine divides over. Sine divided by cosine is tangent. The coefficient of friction to just barely keep something from sliding is equal to the tangent of the angle. That's it. This is a way that you could find the coefficient of friction relatively quickly, and maybe we'll try that in lab and compare it to another example. Okay, this is very similar to the previous problem, but now we have some acceleration down the ramp, and I want to know what that acceleration is. There's still friction in this problem, and so we're going to start with a free body diagram. We literally just drew this, but you could use the practice, so let's do it again. What forces are acting on our block? Gravity is pulling it straight down. The normal force is pushing out of the page. There is some friction. That's it. Okay? Now we're going to tilt our axes again. We're going to say this is our x-axis, and this is our y-axis. And this is our angle. All right, so now we can create our equations, and it's very similar to what we just did in the x direction. We have FGX minus FF. In this case, we're not in equilibrium. This is going to equal MA. This becomes mg sine theta, just like it was, minus mu times normal force, equals MA. No difference from the previous problem yet, except for this MA. Don't know normal force, got to come back over to Y. This is the same as the last problem. Normal force out of the plane minus force due to gravity in the Y direction into the plane. Is it in equilibrium in the Y direction? Yes. It's accelerating only in the X direction here. This is why we tilted our axis, to make this so much easier to do. So the normal force is going to equal FGY. So the normal force is going to equal FG cosine theta. Oh, sorry, that's mg cosine theta. Plug this in over here. We get, this is getting big, mg sine theta minus mu mg cosine theta equals MA. Cool, every term has an M. And let's factor out the G. So we can get G times sine theta minus mu cosine theta equals acceleration. And if you take a look at this, this means that the steeper the angle, the more it's going to accelerate, and that the weaker the coefficient of friction is, the less friction you have, the more it's going to accelerate. This is exactly what it should look like. So there you go. That's 12 sample problems for forces and motion.